a lot of dust in the atmosphere, and it is very important, and because it affects radiation, and it affects chemistry, it affects clouds, and therefore, if we want to understand atmospheric circulation and climate, we should understand how dust behaves. However, relatively little is known about dust. So today we are very fortunate to have as our speaker, Dr. Paul Ginoux from NOAA at Princeton, who really knows more about dust than most atmospheric scientists, and he has worked and very productively in all aspects of dust in the atmosphere. He will show us the very detailed inventory of dust sources he has developed. Then he has worked on transport of dust in the atmosphere and simulating global dust in general circulation models, dust in clouds, and also the impact of dust in the last ice age, and so on and so on. Everything we want to know about dust, and we're afraid to ask, you can ask Paul Ginoux. And so in terms of background, he attended his undergraduate school and the master's degree at the Free University in Brussels in Belgium. And then for his PhD, he worked with Guy Bresser at NCAR. And then he did a postdoctoral study at Goddard Space Flight Center in Maryland, where he actually helped develop their go-kart model. And then over the last few years, he is working at NOAA at Princeton. So let us welcome Paul Ginoux. Paul,
Thank you. Thank you very much for the invitation. It has been a long drive. Crossing New York was really tough, but on the other direction, it was amazing. I never saw such a stuck traffic for 15 miles. It was because of an accident. So I will, as Sultan said, I work on different aspects of dust. I looked at the effect of dust on air quality. So we know that fine particle in the micrometer, particle with micrometer diameters, create some respiratory distress, eye irritation. Of course, they reduce visibility. And I am actually working with Princeton University to look at the effect of dust on developing, producing meningitis outbreak in the meningitis belt, which is in Sahel. And this is a publication from French, Isabelle Chapello and co-authors, where they looked at the correlation between dust outbreaks, the number of cases of dust, and meningitis. So the idea would be to, if we can find a parameterization relating the meningitis outbreaks with dust amount, we will then implement that into a predictive model to help the World Health Organization developing the vaccine in time before the outbreak. Another aspect I've been working is dust effect on ocean biogeochemistry. In the background, you have some diatoms, which are of the order of 1 micrometer. And so these are the phytoplankton blooming in the ocean. And one nutrient they need to develop is iron. And most of the iron you have here on this image, the blooming here in green, and the phytoplanktons. And most of the iron is coming from alluvium deposited by the river. And you have some also some iron coming from upwelling. But in the remote part of the ocean, there is no iron. And the only way they can develop is by getting iron through dust deposition. So you have dust transport, long range, and then deposit over the ocean. And there are some field campaigns showing that, that within a week, if you spray dust, you can have phytoplankton blooming. Another aspect is dust effect on climate. There are different effects, and they are called direct, semi-direct, and indirect. The direct effect is the interaction of the particle and dust with radiation, and dust is scattering and absorbing solar and infrared radiation, mostly absorbing in the infrared. There are some direct effects, semi-direct effect, which is cloud burning by absorbing aerosol. So dust is absorbing solar radiation and will heat the atmosphere, which will burn out clouds. And this is called semi-direct. Then we have the indirect effect, which modify cloud properties. For a given amount of water vapor, if you increase the number of nuclei, you will get smaller cloud droplets. And smaller cloud droplets mean brighter clouds. And so it will increase the apparent reflectivity, the surface reflectivity of the Earth, which will reflect back the solar radiation, so it will have a cooling effect. Because these cloud droplets are smaller, they will precipitate less. And so the lifetime of clouds are longer. So the atmosphere will stay brighter for a longer period of time. So it's cooling the atmosphere. This is very strong effect and are studied in detail. The difficulty is to, in terms of modeling, to simulate the microphysics, cloud and aerosol microphysics. So the uncertainty are very large here. Here the difficulty is mostly in knowing the optical properties of the aerosol. What are the factors modulating the effect of dust on climate and air quality? So dust will contain contain different minerals, and in particular iron, hematite. And as you know, hematite is strongly absorbing, and by absorbing more solar radiation, it will also deliver more bioavailable iron to phytoplankton, and it will, I didn't mention, but we have an effect on ozone chemistry. I have here a modest photo over the Persian Gulf. You have Iraq here, Kuwait, Iran, and Saudi Arabia. And I choose this picture because you see dust plume with different colors. So when people speak about dust and dust effect on radiation, they use one type of optical properties. But as you see, you can see clearly in this picture, it varies from pure white to dark brown. And the dark brown is related to the amount of hematite. You increase by a few percent the amount of hematite, and you go from white to brown. Now, when dust can be emitted when you have cropland or pasture and you have drought, it can be uplifted into the atmosphere. But this dust, I have a paper showing that this dust may be mixed with ammonium salt. And as you know, sea salt, for example, if you go to the ocean, and you will see a sea spray, it's very white, it's very scattering. So instead of having an absorbing dust, dark dust, it will be whitish dust because of the use of fertilizer and manure from cows. You will have some ammonium which will be emitted and co-forming some ammonium nitrate or sulfate on the dust. And you can have this kind of white plume here. So the variability of this factor can be traced back to different sources. So you see this plume can be located back, can be traced back to particular source. So one of the goals, if we want to have some skill in determining, in understanding and to measure, to determine the amount of effect of dust on climate, we need first to know where are the sources. So the first question I am asking is, what are the preferential location of the dust source? Are they everywhere? Is the dust source just the desert? You need arid condition and some sand, and up you have the source, or are the source preferentially located, and where? Now, once you have detect the dust source, we need to know their contribution to global and regional emission. And then we need to know if the dust source are modified by climate change, and are there feedback. So that's the question I will try to answer. And to answer this question, I will first show you an algorithm that we developed to detect the source globally using satellite data. Then we will do an attribution. Knowing where are the dust sources, we will try to attribute if they are natural, so no human activities, no cropland, no pasture, or they are related to some agriculture. And then I would like to know also if they are coming from ephemeral lakes, which are really, you will see, preferential dust source. So for that, we will use some ancillary data. Then knowing the dust source and their origin, we will use a model to calculate the emission of each source, and then we can look at the contribution from each of them to global emission. Some feedback, some background about dust. Dust emission. If the dust particles in the atmosphere are less than 10 micrometers, okay, and dust particles less than 10 micrometers are either clay or silt, not sand. Sand are larger, and they cannot stay longer in the atmosphere because of gravitational settling. Now, if you have a nice piece of clay or silt and you blow as much as you can, there will be no emission of dust, because there is a cohesive force between the clay particle. And it has been shown by field campaign, field data, and wind tunnel that in fact the process to have dust emission into the atmosphere is a sand blasting process. Because your sand particles are relatively light. Here I have a soil, okay, with sand particle resting at the surface, and of a silt and clay surface here. So the wind will pick up, will move this sand particle, but it's too heavy to be uplifted in the atmosphere, and so it will drop back on the surface, and it will create a sand blasting process, which will emit then the fine particles, which are so small, less than 1 micrometer, that any eddies can uplift them during the day. When you have a fully developed boundary layer, you will get turbulent eddies which can entrain this particle in the atmosphere, and then you have the trade winds bringing them over long distance. So the way the dust emission is calculated is you need first to calculate an horizontal flux of sand, and then from that you can calculate a vertical flux of dust. Okay, and what I want you to see is that the dependency of dust emission, sand emission, is at the cubic power of the friction velocity. Okay, so it's a very strong function of surface winds, u cube. And then you have this term here, which vary from 0, phi, which vary from 0 to 1. It's 0 when the friction velocity is less than a certain threshold velocity, which is a function of soil moisture, roughness element. You have any vegetation, it will increase this UT here, the threshold for wind erosion will increase dramatically, and you don't have any transport of sand, horizontal flux of sand, and so no vertical flux of clay. Okay. What are the global emissions? We are speaking about 2 billion of tons per year. Okay. So a ton, it's a SUV, so you have like 2 billion of SUV in the atmosphere per year. Okay. And But the SUV will fall back rapidly while you just stay for days, about a week. Yeah, here I have the lifetime for 5-7 days. Sorry. There is strong variability in this emission. The ice core data show that during the last glacial maximum 25,000 years ago, there were more than 20 times more dust in the atmosphere, up to 100 times more in Greenland, 20 in Antarctica. So all the effects that we are studying, the effect on radiation, phytoplanktons, blooming, effect on clouds, are amplified during the LGM. So dust, if you look at LGM, you need to include dust. And nobody is actually doing that, but we know at GFDL have done a simulation of LGM, and we will implement dust and see the feedbacks, which will be the first time this has been done interactively.
So is there a simple explanation for this?
I developed with a student a theory which seems to, well, it seems that the increase in Antarctica, the main reason is the sea level which has changed, and you have some continental shelves which have been exposed, and then you have this, because there is no vegetation on that, it's very dry, conditioned, so it's excellent resource.
The winds are so much stronger.
Yeah. And you get this factor 20. So we did a test, present LGM, and compare the two at different ice cores, and we could explain most of this ice core. But it varies. This is from Patagonia, the dust from Patagonia. So this is for, this is not true everywhere. In the sector influenced by Australia, it's much less pronounced, this increase. So from that, I tried to see, well, if this is true, it should be true in Greenland. And I did the time series of dust emission using isostatic adjustment, and so the continental shelf appearing, and I have a source function, and I could reproduce 20,000, 25,000 when they are correlated. If I have the dust concentration in ice core, it follows exactly my amount of dust emission. So it seems to work both in Antarctica and Greenland still. The size distribution is dust is between 0, 1, and 10 micrometer, because all the dust larger than 10 micrometer are removed by gravitational settling. An important property of the, here I have the volume size distribution from sun photometer data published by Dubovik et al. In 2002. So you have the, in y-axis the volume size distribution, and x-axis the radius from 0, 1 to 10 at different location. I don't have the name here, but I can tell you this is Cape Bahrain, at Bahrain and Cape Verde, and another dusty region. I forget, this may be in Asia, Taklamakan. But the point here is that you have this coarse mode. This is called, everything greater than 1 is called coarse mode, okay, and this is the accumulation mode, because the particle will accumulate. And this has mostly sulfate pollutants, organics, and some black carbon, while here it's mostly dust or sea salt. An important property of dust is, I mentioned, it's absorbing, but you have to be careful, it's absorbing a certain wavelength. It's transparent at all. And so if you go in the near infrared, if you try to measure aerosol at 1 micrometer, you will not see them. You will not see any aerosol. And so what I show you here, it's called the imaginary part of the refractive index. Okay, the refractive index, you have seen that in Optical. So it's telling you the amount of absorption. And the value vary by a factor 10 here. So I have 0.01, and I have here 10 minus 3. So and on the x-axis, I have the wavelength. 500, that's clean. Okay, 1000, that's the near infrared, and then we have the infrared. And so the amount of absorption decreases with wavelength. So it's very absorbing in the blue, and it doesn't go to the ultraviolet, but it's even more. So if I continue this line here, it will be increasing like this. Strongly absorbing in UV, in the blue, and then it's decreasing in the red. It will start to be transparent, and in the near infrared, nothing. And then you have at 10 micrometer, a big peak of absorption. So it's absorbing at 9.6 micrometer too. So if you have an instrument and you want to measure dust, what will you do? You will go where it's absorbing, not where it's transparent. So some people are using in the infrared with a band at 9.6 micrometer, or in the ultraviolet, or in the visible, but using the blue. Okay? So if you want to use satellite data, you want to detect dust source. You want high spatial resolution, you want high temporal resolution to capture the development of dust event, and long-term record to create some robust statistics, and then you want the spectral variation of optical properties. So the best would be to have one in the ultraviolet, blue, green, near infrared, and 9.6. Then you can really be sure that it's dust. Because only dust has this spectral variation of absorption. Okay? And so I will go quickly through the history of use of satellite data to detect dust source. From one channel, at almost the red, to TOMS ultraviolet, to MODIS multiple wavelengths. And you will see that we improve quite a lot the detection of dust source as we increase the number of bands of backscatter gradiences of the satellite instrument. This is a paper published by Rao et al. In '88, and it shows here the absorption optical depth, which is a measure of the attenuation of light, and you see for the different seasons. And so it varies from 0 to 1 or so. And you see some maxima on the west coast of Africa or the Atlantic here, and it varies by season. Here in winter, it's around 5 degrees north, and then it moves to 20 degrees north in summer. Okay? So this was the first time we saw that aerosol were transported from one continent to another from satellite data. Nobody knew that dust were transported here. I can tell you a funny story about Barbados later. So Inat Hagen and Ines Fung were developing the first dust model, global dust model. And they try to know where are the dust sources. They have no clue. From this, you cannot know. So they use the FAO soil maps, which telling you how much clay and silt you have, and they said all the clay and silt from desert can be uplifted into the atmosphere using the emission dependence of cubic power surface winds, and they simulate that, and then they compare with this AVHR data. And it failed. So it was a failure. Most essentially, they were unable to reproduce this variation of this change of the dust plume, of this aerosol plume, from southern position in winter and northernmost position in summer. So what they did is they add some additional source in Sahel, up to 50%, and boom, then they could reproduce that variation, seasonal variation of the dust plume. Okay. Then we, with the TOMS ozone mapping spectrometer, the TOMS ozone mapping spectrometer is an instrument dedicated to measure ozone. So it's in the ultraviolet. The NASA want to monitor the ozone hole, okay, which appeared in the 70s. And so they launched this satellite and they tried to monitor ozone. But I told you dust is absorbing ultraviolet, so they were annoyed by this noise, which was coming from from dust. And German at NASA Goddard had an idea, and he said, why don't we use this noise to detect dust of absorbing aerosols? Because black carbon is also absorbing in the visible, as you know, it's black, and also in the ultraviolet. And he defined an aerosol index, which is the difference between ratio of measured radiances at 2 wavelengths minus the ratio of the radiances calculated for a purely molecular atmosphere. So if you have no aerosol, then your measurement should fit the calculated, because you will get only scattering and absorption from molecules. The difference will be related to the presence of aerosol. And in the case of absorbing aerosol, you will get a positive value, and if it's scattering aerosol, it will be negative. So this index is telling you, and I show you here, the distribution of this aerosol index, positive value, absorbing aerosol for 3 days in 1988, in March 1988. And so you see this aerosol coming from Sahara and transport to Europe, and then it's turning around and going to Bermuda. Okay, this could be used to detect, and was used to detect, the origin of dust throughout the world. The problem with SoMAS is that it's low resolution. At nadir, so when it looks vertically, it's 50 by 50 kilometers. Off nadir, it's 250 kilometers. Over a 250 kilometer by 50 kilometer rectangle, the probability that we have a cloud in it is very high, as you can imagine. Aha! If you have a cloud in it, the pixel will not detect it, and you will say, this is a very bright surface, and so it will amplify the backscatter radiances, and so it will increase artificially the amount of your signal, the backscattering. So you will get very high aerosol index, and this is not because of the amount of aerosol, but because of change of surface albedo. Because you are in the ultraviolet, you have molecular scattering. Okay, and molecular scattering, as you know, the number of molecules is a function of pressure, and so you need to know where is your aerosol vertically. So you need to know the vertical distribution of aerosol, and from an instrument which is looking at the column, you don't have this information. So you need ancillary data to know the altitude of your aerosol. And there is a weak signal to noise ratio near the surface. However, also there is all this problem with some Joe Prospero University of Miami, myself and colleagues. We looked at the daily value of aerosol index and searched where there were maxima. And we said, where there is maxima, it's where are the dust source, because of mass conservation. The maxima can be only over the dust source, assuming that there is no dependency on the altitude, which is wrong, and cloud contamination, which is also wrong. But what the main point of this paper, which is published in Review of Geophysics, and this was the first time it was shown that there is preferential location of the source. They are not located in deserts. They are located in topographic depression. And the reason is that it's where you find alluvium. So each laser contour is telling you where this aerosol index is greater than a certain threshold, whatever the value. And the frequency, the number of days per year, the aerosol index is greater than this threshold. And the maxima are located, and in the background is the shading is the topography. And all the maxima are located in dark green. This is the Bodily depression. Here it's a depression in Mali. This is the region of Chad in Tunisia and Algeria. in Libya, everywhere, it's always in dark green. Here you have the Indus, the Taklamakan, everywhere. We found that everywhere around the world. And it's either because you have present time, like this was a lake like 10,000 years ago. It was filled with water, and so you have you can still find some diatoms over there at the bottom here in this region, and the plume coming out of that are very white because of the presence of diatoms. So you have, because of these lakes or weathering of surrounding mountains, you have a transport of alluvium, clay, and silt down to the bottom of this depression. So those sources are located preferentially in topographic depression. Okay? This was the major results of this paper. I have the wrong one. But in terms of modeling, what we did is we developed a way to take into account this preferential location to simulate dust. Instead of saying every desert is good, we said no. We have a source function which varies from 0 to 1, and it's based on topography. And we calibrate this function using the TOMS, the Prospero et al. Paper of 2002. And we came up with this source function, which is now used by most models. A few years later, the problem of this source function, it was quite empirical. So it was not really physically based. So Inate again came up with something more physically based, also Charlie Zander, and a student of Charlie Zander. And so they came up with different sources, but fundamentally it was based on this topographic depression ID, and then to, instead of having everyone, Charlie, myself, and Ina saying, my source is better, we try to be more objective, and we use some least square method and comparative observation to find the error of the model simulation compared to observation. And here I show you this, the results of this paper by Rea Kapoor et al., published in 2006. So we did a many simulation, and then calculate the error based on the this y-axis is the silt emission, and the x-axis is clay emission. And you have the error here, and the gray is telling you how much you have error. And the smallest, this ellipse, the smallest the error. Okay, so that was nice. We now know where are the dust sources. However, when you look at this photo, this is a photo of in Mauritania, I forget when, doesn't matter. And I overplot in the black contour are the ephemeral lakes. And it's extraordinary to see that these dust plumes are coming within the depression from these lakes. And this is the famous Bodily depression. I mentioned you how white it is. It's because it contains diatoms, okay? But here it's not as white, but you have the dust plume. And this is the isocontour of the ephemeral lakes over the region, and you see it's really coming from these ephemeral lakes. The problem, we couldn't detect if the dust source were coming within the depression from a lake, because TOMS resolution is 50 by 50 kilometers at best, and this is 50 by 50 kilometers compared to the region. So you see, no way we could detect this source. So we need a much higher resolution to make attribution. Another problem is, so this aerosol index is a measure of absorbing aerosol, and there are other absorbing aerosol in the ultraviolet and dust, particularly organic carbon, black carbon. And so we had to limit ourselves in region where we were sure there was no black carbon and organic carbon. So we cut off here. The problem is that if there is anthropogenic dust coming from agriculture, cropland, pasture, it's coming from this region where you have human activities, where you have biomass burning. So there is no way you can detect that if you cannot filter out organic carbon and black carbon. Okay? So a way to do it is by using the signature, the absorbing signature of dust, and using multiple wavelengths from a satellite instrument, eliminate, filter out everything which is not dust. Okay? And that's the idea. So the idea, we know that dust is coarse mode, okay? And there is a fantastic measure of this size distribution, which is called Angstrom exponent. If you take the ratio of two optical depths and you divide by the ratio of their wavelengths, this alpha value varies from 4 for molecules to negative value for particles greater than 1 micrometer. Yes, right. If you calculate that, this value. So if you have negative Angstrom exponent, you are sure that your particles are mostly in the coarse mode, greater than 1 micrometer. Okay, so the first criteria is using this alpha less than 0.5. Then this is coming from again the Dubovik et al. Paper, where he showed the absorption property through the single scattering albedo, which is telling you the amount of scattering versus the total extension, absorption and scattering. So it's the opposite of the imaginary part of the refractive index. I show you dust is at shorter wavelength is high and it's decreasing and transparent at the near infrared. The single scattering albedo is the opposite. And when your aerosol is transparent, there is no absorption, no scattering, it will be 1. Okay? And as you increase the absorption, the denominator increase, and so this single scattering albedo decrease. And these are the single scattering albedo at 440, 550, 670, so blue, green, red, and in near infrared at different locations. So dust has this particular property of increased single scattering albedo with wavelengths and is mostly in the coarse mode. So if you use these two criteria, so what you want is a positive slope of the single scattering albedo for up to wavelength. So we developed 3 criteria to extract dust optical depth from modest deep blue. We use negative Angstrom exposure to have coarse mode particles, increase single scattering albedo with wavelength, and we want some absorption in the blue because we know dust is absorbing the blue. So we use the modest deep blue product, which has been developed by Christina Shu at NASA Goddard. MODIS is a polar orbiting sensing from with a SWAT of more than 2,000 kilometers. There are 2 MODIS instruments, one on Aqua at 1:30 p.m. and one on Terra at 10 a.m. Equatorial passing time. The level 2 resolution is still 10 kilometers, so we go from 50 kilometer distance to 10 kilometers. And the good thing is it has spectral product, the optical depth and single scattering albedo at this 3 wavelength, and they calculate at 550, but it's mostly measured at 3 wavelengths. So we have what we want. We have high resolution, and we have the spectral variation of optical properties. So I will show you here over the Arabian Peninsula the way we use this criteria to screen dust. So we have a view here for March 20, 2012, aerosol optical depth with a peak here in Yemen and some Iran border. And then the Angstrom exponent, the blue is negative, so coarse mode particle, and the red fine mode, so you have some fine mode. So we keep only the scene, the pixel where there is blue for value here for Angstrom, and we want positive when it's red And in fact, it's increasing single scattering albedo with wavelength everywhere. So using these criteria and some absorption, we extract from aerosol optical depth, dust optical depth. So we are sure that within this scene, the dust is dominating the aerosol optical depth in this region. That's the trick. We do that for every single granule, okay, and for every day, for every year, for 10 years. Lot of work. And this is the resulting global mean, annual mean, modest D blue, aerosol optical depth, and dust optical depth. I plot first the aerosol optical depth in blue, varying from 0.05 to 1, and then I overplot dust optical depth from with the same value. So if the dust optical depth is less than 0.05, then you don't see it here. You can have dust, but you don't see it. So we see that the dust optical depth is in the Sahel-Sahara region, the region of Chad, Libya, Mesopotamia, Iran border. That's interesting. A lot of dust here in India. Pakistan, Taklamakan, of course. We have the Aral Sea. We know now it desiccates, so it's a big dust source. And the Lake Erie region, famous dust source. We have some Namibian dust source in here. I forget the name of this one. It's which one? Kalahari. Yeah. But the name of this lake is it's long anyway. So we have some Takama region and Peru, and also in the Mojave Desert and in Texas, in California. Okay, so this seems to work. I cannot show you the validation because of time, so I spent time validating that with spectrometers and comparing different algorithms. I will just show you the comparison with the TOMS and what is the source. The shading, red shading is the modest D blue frequency of occurrence that the optical depth is greater than 0.2, and the green contour is the aerosol index measured by OMI, which is a TOMS type satellite, greater than 0.5, and the blue is TOMS. And so these are the ISO contour, and the peak are located here over the body, and the models show that also in Mali region and the region of Chad, Libya, Mesopotamia, Gange Basin, Indus Basin, Taklamakan, Caspian Sea, Aral. The difference is here in East China. OMI shows more dust than modest D blue. Otherwise, in Australia, it's very similar. Here it was more pronounced with storms over South Namibia. Patagonia, this not shown by TOMS. Otherwise, all the sources in northern in US are matching, except here in the high plains, and I will focus on that, and I am now focused on that, really in terms of modeling. Yeah.
You're calling it sources, but it looks to me like it's amount, not sources.
No, it's the amount of optical depth, yeah.
So then why didn't you have that over the ocean if it's optical depth?
Because the algorithm retrieves only over bright surface. If the surface reflectivity is greater than 0.3. So no retrieval of forest over ocean for this modest instrument. On sea waves, Christina Schuh retrieve globally. She goes bright and dark surface. No, wait. This is the frequency of, it's not the amount, this is the frequency of occurrence. This is amount. This is the total amount of annual global mean, annual mean. But here it's a frequency of occurrence. It's not the same, right? So the red is the high frequency, is the region with high frequency of dust optical depth greater than 0.2.
Okay, so it's a frequency
of occurrence.
Amount. Frequency of occurrence of amount.
Yeah. So no attribution. So I will use ancillary data to determine if this each pixel, if they are collocated with cropland or pasture, and I will use Klein-Gerd weight data set, which is also at 10 by 10 kilometer, and I will see if there is any ephemeral water body, and for that I use MODIS 1 kilometer resolution data. I will show you only, this is the percentage of land use and pasture plus cropland from Klein-Gerd weight. The green, so it's telling you that the dark green is 100% of the surface is land use. You have cropland. And red, pasture. And when it's red, dark red here, it's 100%. So the entirety of the grid cell is occupied by land use. I showed that I was there in Coast, King Abdullah Science of Technology Center in Jeddah, and I went also to show that this is totally wrong. This is a desert. You know, and this is the empty quarter. Nobody is living. You no way you can live there. And this is you. So then, why you use that? There is another one, much better, by Raman Kuti. I use that because this is used by RPCC. And this is really the most dramatic problem. The other one is in Australia. It's totally wrong. You have like kangaroos everywhere in Australia. It's wrong. Otherwise, it's working with Raman Kuti. But it's unbelievable that they publish that, and they provide that, and it's totally wrong. And here I have the distribution of ephemeral lakes, and that makes a lot of sense. Well, this is what NASA product.
So could you go back again? How did they get the...
They use satellite data and local
with
data.
DPI, with
Yeah.
what?
But I mean, there is nothing.
Okay.
So this is from the Netherlands, where it's very clean. I mean, this is unbelievable today. No sense of reality here. So, but it's to tell you what show, but I was forced to use that because it was used by IPCC. So this is my dust source with attribution. The blue are the percentage of time there is dust in the atmosphere from hydrographic source, from natural source in red, and magenta anthropogenic. And so because of this wrong ancillary data, all my dust source in Saudi Arabia is anthropogenic. I don't believe that. Only here I have some natural source and Iran, and strangely in Mesopotamia, where there is a lot of agriculture, it's natural. So but here it makes sense. So you have a lot of blue, that makes sense, ephemeral lakes. Okay, I am going very fast now. So I calculate the emission, and so this is, so I use high resolution model to calculate the emission, and the blue show the natural emission, and the red the anthropogenic emission in gram per square meter per year. And so in Sahara, it's mostly natural. In Sahel, you have a little bit of dust emission in Sahel, in Central Asia, India. Lake Erie, it's anthropogenic dust, but we know that's wrong. Patagonia, we believe that a lot of pasture there. And also some anthropogenic, you barely see it, I'm sorry, but in the high plains there is dust. So if we calculate the the regional mean value of emission, dust emission, this is 900 teragram per year. I told you the global is about 1500 teragram per year. So 90% of the dust of 800 teragram is from natural, and only 8% anthropogenic in Sahel, with a total reaching 2/3 of the global emission. Because of that, because most of the dust is Sahara natural, and Africa is a major dust emitter, globally anthropogenic dust account for 25%. But in other regions, like in North America, it's 50-50. We know Australia, here it's 75%, but this is way overestimated. And Central Asia, 50-50. But so the contribution of anthropogenic dust is much larger.
So the distinction between the two depends primarily on the surface type.
Yeah, domiciliary data.
Okay.
Yeah.
Which is prescribed.
Yeah, normally they use data from the country, mapped, satellite. So what I found interesting is when now I am looking at the presence of ephemeral lakes, and what I found is that the anthropogenic dust. So here I have for each continents the natural emission and the anthropogenic emission. I have the contribution from ephemeral lakes, the blue in blue. So for natural source, the contribution of ephemeral lakes is relatively minor. But for anthropogenic, it's 80%. And that makes sense, because if you have cropland or pasture, you need water. And the cattle need water. So that's important, because it means that the anthropogenic sources are sensitive to hydrological cycle, and therefore to climate change. So that's a big result of this study. And I will show you, this is the first time, I think, and the first time that an anthropogenic dust source has been simulated. This was continental scale. This was in October 18, it started in 18 October 2012. And it's shutting down, look at that. This is in Oklahoma, Tulsa. This is a view from Modis, October 18, and Nebraska, South Dakota, and you have this dust storm here. This is Kansas, Oklahoma is south of that. So it's telling you the dimension of this view with accident here created. This is a photo in Tulsa. Look at it. It was so bad they had to shut down the interstate highway. We never spoke about that here. But this kind of event happened all the time in the southern southwest US. Okay, and so everybody is focusing on Africa, Asia, and nobody is looking at that. And I would like to understand the characteristic of this anthropogenic dust source. I use this embodies the blue dust source with an high resolution model, 50 kilometer global, and I show you here for 4 days sorry, the evolution of dust optical depth only. The model contains all the aerosol, it's a climate model. But I show only the dust optical depth, and the contour, the shading is the optical depth, and the contour are the emission. Okay, and it's in Nebraska, and it goes also in Wyoming. On the next day, it moved south, and then 2 days later, it was here. I show rapidly a comparison with Spectrometer at CART site, DOE site. This is the aerosol optical depth with the time series. The little dots are the observed optical depth. The value of optical depth by Spectrometer is fantastic, 0.02. Okay, the error is very small. And this is varying from 0 to 0.2. So this is very precise data. The gray dots are the model optical depth, all aerosol. The red dots are dust only optical depth. So no dust, and then suddenly on the 18, it increased, and it's contributing 100% of the total optical depth, and then on the 21, it stopped at CART site, which is in Oklahoma. Okay, and I show you here the Angstrom exposure. When dust is increasing, it drops. As I mentioned, it's going negative when you have very coarse small particles, and you see all the time. And then when dust disappears, it's increasing. And I compare also at Georgia Tech. We have a problem here because it's a climate model. Except for dust, which is calculated interactively in CISOL, all the fire emission are climatology. So if it's not the right time, I cannot be perfect here. But so if you look at CART side, it's matching quite dramatically well, and at COVE also, I may be overestimating here. Okay, I look at Calliope data, and also Calliope data, it's a LiDAR in space showing the dust at the right moment. Now, the big things of that. I will zoom out. This is my isocontour of emission, and I zoom out here, and this is showing you at 30-meter resolution by the USDA. Every year, farmers have to report what type of crop we use. You can zoom here in Long Island. You will see if you have a farm neighbor, I do in New Jersey, I can see what crop is doing every year. Anyway, the yellow is corn. Aha. So in the middle of night, the sur here is corn. You know that there was a drought. Okay, and you have to know that people want to develop more cornfields for biofuel because that's the way the future is for farmers. So it's very important to know what will be. So this is showing you that dust after a drought in the northern night winds has produced a continental scale dust storm. Okay, and now it's important to know if this was true in the past or it's just random. And so I plan to use, because this USDA have this map for years. And so using the modest D blue, I want to see if the maxima of modest D blue is all dust optical depth is located with corn. And that's some consequence. So I will conclude here, yeah, and I look at the, I look also in the future of drought. And so in the southwest we will get more dust, and the northwest less dust event. So globally, anthropogenic source account for 25%, with the lowest in North Africa. Emission from ephemeral lakes contribute globally 30%, but anthropogenic sources are generally associated with lake. 80% of sources are associated with lakes. So this suggests a sensitivity of anthropogenic source to hydrological cycle and climate change. Anthropogenic dust in the high plains appear related to cornfields, which are sensitive to drought, as shown by last year's crop failure, followed by continental scale dust storm from Nebraska. Climate models predict an increased dryness in western US, which may be associated to increase of dust event, especially if some type of crops extend. And thank you, and you have here a movie, 3 lines using our high resolution, 50 kilometer resolution, showing the optical depth. Each aerosol has its own color. Red for dust, gray for sulfate, carbonaceous aerosol green, and sisal blue. And this is for 2012, and you will see Sandy, Hurricane Sandy, producing in October. When you reach October, we are in March now. First, you will see the October dust plume occupying everything, and then you will see Sandy coming and going to New Jersey and producing a lot of sea salt and sulfate. Okay, I will take any questions.
You want people to watch the movie and let it finish?
Sure. But it's looping.
No, it's not. Any questions for Paul Ginoux? Yes. Steve with a question.
Yeah, fascinating talk.
Thank you.
I'm coming away with the sense that what we don't know exceeds what we know. Is that accurate?
At which level?
Well, I'm interested in forcing. You keep talking about anthropogenic.
Yeah,
And
exactly.
really the issue is not so much anthropogenic, but secular. As a function of time, what is the change in the radiation balance from some reference point due to, no, not anthropogenic, due to dust? Because that's the number. We want this as a function of time. We don't care whether it's human or, for the purpose of modeling, we don't care if it's human.
No, for IPCC they want to know if it's anthropogenic, but if it's not.
I don't care about IPCC. If you're trying to model the secular change of temperature and other climate variables, you need to know the secular change of dust forcing.
Yeah.
And my question would be, in your heart of hearts, how accurate do you think the secular change in radiative balance due to dust is known?
Okay, the only modeling study was done that it's not any amount. Okay, by forcing a model is data. The problem, if you want to do that with a model, is you need to take into account the vegetation, and land use change, and soil moisture. And nobody has done that interactively. I have been working for the last year with people in land model at GLTL, and we came up with a code. I will present the result in the Paul Schmidt conference in Firenze, and promising in the. So what you have, so you have generally model, atmospheric model, okay, and then you have what's called a flux
Could
exchange.
you put a light on this, Hilton?
So the way the climate model is that you have the atmosphere, which has changed flux, okay, with the what's called a flux exchange, because the atmosphere model has different grid than the ocean. This one is regular grid, this one is tripolar, so they exchange it. And so everybody is calculating dust emission here. So if you want to take into account vegetation, you have to pass that through this flux exchange here. But you need a lot of variables, because there are so many variables. You cannot look at LA, it's wrong. If you do that, Canada is a bigger source. You have to take into account the cells and the sticks and everything, and the dead units will be wrong. While the model is doing that. So the idea was to move here the flux. So we moved the calculation of dust emission into the land model, and LM3 as the particularity is that a grid cell is divided into tiles. So it's some subgrid which include primary vegetation, secondary vegetation, cropland, pasture, lakes, glacier. And you calculate everything is calculated within a time. And then you take the mean of the value and pass the flux to the atmosphere. Instead of passing mean value to the atmosphere. This has big importance, okay? Because if you have a little bit of vegetated surface cropland, and you take the mean value of vegetation over your surface, you may overestimate dust emission, of course. So we did that. On top of that, because this was developed for CO2, they parameterized the position on surface and leaves. So I use all this parameterization for aerosol, I adapt for aerosol, and so now it's working. And so I have done 50 years, 60 year simulation, and also one with pre-analysis, and then 100 year with observe SST. And I could simulate, I could see reproduce the dust of Arcturus with the glow dust in the 60s. I could reproduce the sharp drop of dust in Australia in 1974, 2012 by P, and it stayed like that for much more. Increase of dust from Patagonia. So that's the only station. But so it seems working. So so by moving the dust emission to a dynamic land model, of course it depends now on your strong land model. If your land model is wrong, you are totally wrong. That's true. But it seems to work.
But I didn't hear a number.
There's so much more to that.
But so what you want is to reproduce the observed amount of dust, right?
No, I want to know radiative impact.
So
You want the radiative impact, but if you have the right amount, you still need to know the optical properties. So that's another business. Because apparently anthropogenic dust is more scattering than natural dust. So we are not out of the wood.
So there's another question.
Yeah, so this actually answered partially my question regarding the subgrade scale distribution of the heterogeneity. Therefore, the soil moisture is also from these patches.
Exactly.
Okay.
Yeah.
Now then, this figure, is it nudged toward reanalysis or it's a free run?
No, this is it's nudged toward the reanalysis. Otherwise, I could not.
Otherwise, you won't
Right.
get
Yeah, you won't get the hurricane.
So then, has this been like compared with observation, with the satellite data?
Yeah, I show you one with the dust plume out of sand. Here we have automatically, we produce comparison. All climate simulation are automatically compared with observation.
So
Some photometers
it's
set
good,
up.
is that right?
Pardon me?
Is it good when you compare with the satellite?
Yeah, it's published in Donner et al.
Okay.
Journal of Climate.
Just one second.
Could you talk a little more about Australia? I think you said that the relative fraction of anthropogenic sources was the highest in the world,
Yeah.
and yet the natural contribution is very low. Why is that? I mean, as a continent that's very dry.
No, this is what I am telling you. It's because the land use data set is wrong.
It's wrong.
Yeah. Yeah, you can smile at me, but I have to.
No,
No, but you are right, and I'm honest here. Yeah, it's wrong. I don't believe Lake Erie. I mean, you have seen photo of Lake Erie? There is no cropland, no pasture. There's nothing. It's just rivers. So it's wrong.
So is that because of lack of measurements, or
The way they do this retrieval.
Just one second. Kamazima has a
So
question.
there is another data set by Hannah Foley from McLean. She's way better. They don't have this.
so why would anthropogenic sources be so high? Just thinking about it. I mean, I'm not from Australia.
Oh, you are from Israel?
No.
Huh?
You can say it's all the bad things you want, but I mean, it's a country that's hot. I mean, it doesn't have. I mean, is it burning a lot of
So
coal?
by looking at this deep blue, I found that the Darwin River here appears as a dust source. And so in the paper review of Geophysical, we discussed that the flow was a third of it was because of drought. So you have this river now that you can see from space producing a lot of dust. So that's anthropogenic. And then in this region, the south east, that's agriculture. That's for sure. So the dust coming from there. But in central Lake Erie region, that I don't believe there is.
You should go down there and work there for a year.
Yeah.
So, Paul, there is one more question here from Kamazima.
Yeah, I was surprised on the two places where I expected to see sources of dust, like in the Kalahari and the Gobi. They were kind of very small, almost too small. And what could be done to rectify that?
So I am not going to rectify. There is a misconception there. Dust event in Africa is all the time. It's high frequency. Dust event in Asia, it's weekly or 2 weekly for only in spring. So the frequency is very low. But when I look at the statistics of dust optical distribution in Asia, it's infrequent, very high dust event. Much more than in Africa, where you have more but less optical wave. So this is why you don't have. You have to look at the cutoff of the frequency of occurrence. You don't have a lot of dust event from you. So there is a misconception to believe that dust is it's big, but it's not.
Actually, sir, one should read this paper and the reviews of Geophysical explains the algorithm review. So the whole idea is that traditionally we think that wherever there is a desert, there should be a big dust source. It's not like that. So
But what worries me was the British are they're putting a lot of money in the emission of dust from Kalahari. That could be wrong.
Yeah, I'm right. Yeah. No, they're not wrong, but it's very small. It's small source, and they have a paper. I was a reviewer mentioning that dust source from the Kalahari is going to Antarctica. I don't believe it's way too lower latitude. Dust you have to go at high latitude like Patagonia, with some Australia to get to Antarctica. So their interest is just out of there to Antarctica. Southern Ocean. I mean, it's there. It's so. But
Margaret has a question.
What is the reason for the correlation between meningitis and the dust occurrences?
good question. We are not sure. But it's funny because I asked questions to these people and they can't know what you don't know. Because, okay, dust contains iron, and this bacteria needs iron to develop. So I was wondering if this could be an element. There is the irritation factor when you have fine particles. So it's because the meningitis is always there,
Yeah.
just need to develop. So you need an irritant, and dust and dryness appear as a good irritant. But I was wondering how much is due to this iron content, and also if it's dust from cropland, it will contain sulfates, some acids. So but we don't know. And so I asked them about because they said it's not you can be only contaminated through saliva. Do you know the death rate of them? Are they sensitive to relativity, UV? Do you know the death rate to UV? No. So it's very